Okay, so welcome back, and this is where we actually stopped in the last lecture. So the very important aspect in this course on microprocessor systems design and interfacing is the knowledge of how to program the device, right? So we all know that we're talking about ARM Cortex M0 Plus, and we also know that the way to program the microprocessor or a microcontroller is two ways. One is actually to directly code in assembly, or you can use C to code your programs. So we'll start with assembly, and we also know that the ARM series of microprocessors or microcontrollers is quite an exhaustive one, and this actually this chart actually sort of nicely captures the meaning of that. So compared to something like a Cortex M4 or Cortex M4F or Cortex M3, the Cortex M0 or M0 Plus series has very limited set of instructions. Okay, so roughly around 56 instructions we do have. So we will dig deep into some of these instructions. Of course, going through each and every instruction is utterly boring, but I'll introduce the types of instructions, some sample examples, and then move on. Okay, so you can always try all these what we are talking about in the Keel Microvision software and experiment with all these things so that you will learn. Okay, so it's otherwise if you just simply read the document or read these lectures or hear to these lectures, you won't be understanding anything. I mean, just like you may get a picture, but it won't become complete unless you make your hands dirty. Okay, so moving on, the ARM itself, if you consider the Cortex M0 Plus or rather the ARM itself, the early ARM instructions were actually 32-bit. So it was purely 32-bit, and it was really powerful and has good performance. I've shown you in the previous lecture comparison between an 8-bit and a 32-bit case where everything was sort of saved off. But then of course we know that with 32-bit instruction comes a bit of complicated hardware circuitry as well as program memory compared to an 8-bit or a 16-bit microprocessor. When we say program memory, it's all about the size of the memory, right? Because it's all 32-bit instructions, so it occupies quite big compared to, of course it's a trade-off because you need more number of instructions in the case of 8-bit or 16-bit, but the program memory, when we say, is actually on the consideration of executing a 32-bit instruction, because you need to always put into the bus or the memory the 32-bit instructions. So it is not like smaller instructions, so it occupies a bigger footprint both in terms of hardware circuitry as well as the bus architecture. Okay, and of course larger power consumption, because we already know that more number of bits is good for accuracy but not good for the area as well as the power consumption perspective. Later on in 1995, ARM introduced 16-bit instructions also. Okay, so this is like compared to 32-bit architecture, this gives better code density because it's just smaller size, and then we already know the code size is reduced by 30%. But performance, obviously we know that a 32-bit multiplication, if you use 16-bit instruction, it requires more cycles, right? So the performance is reduced by 20%. And then again some revision happened, and people call it as thumb 2. The 16-bit was known as thumb 1 instruction because the original was 32-bit, so it is like you only have a subset of it. That's a literal meaning of it, so they used to call it as thumb 1 instruction. And then later on they called it as thumb 2, where it is like you are like 116 and another 16 together, so you have two thumbs together. So it's a mix of 32-bit and 16-bit instructions. So how does that work through is like you have the incoming instruction, there is a hardware circuitry which is done for you. You don't have to do anything, it is already done for you. Don't even know. You remember the T bit in the special register in the previous week, please go back and see that again. So this is to distinguish between the thumb 1 and thumb 2 instruction. So we can actually have 32-bit instruction execution possibility as well as 16-bit instruction execution possibility. So you need to have the hardware circuitry supporting those two, so that's a complexity associated with it. But having said that, this is the modern trend, the thumb 2. Cortex M0 Plus also you will see that will have thumb 1 and thumb 2 instructions. It's a mix, sorry, actually it's a thumb 2 instruction, but it's a mix of 16 and 32-bit instructions. Okay, so thumb2 in a nutshell is like it has both 32-bit and 16-bit. The code size is reduced to 26% compared to the original 32-bit while keeping a similar performance. That's a key aspect. Literally it says that you don't really need 32-bit instructions all the time. You can well live with 16-bit instructions, but few cases it's better to have 32-bit instructions, and thumb2 has that capacity of potentially having the best of two worlds. Okay, so best of 16-bit and best of 32-bit. Okay, so this is the pictorial way to represent it. ARM instruction, or the conventional ARM instruction, is all about 32 bits. Thumb1 or thumb instruction is all about 16 bits. Thumb2, which is the modern day trend, is all about a mix of both 32-bit and 16-bit. You might be thinking, why not 8-bit? So that's not considered. Maybe it was considered and they might felt like it's not really useful. Okay, so they settled down on the 16-32-bit combinations. So in a Cortex M0 Plus case, these are the 16-bit instructions which are supported, and these are the 32-bit instructions supported. So some of the BL means branch. So some of these are all special move instructions. Okay, move to special register, so sort of instructions. So some of them we will work out, we will use, but mostly we will be using the 16-bit instruction. So we will study in detail what each one of these means, at least as a group. So essentially we will have a subset of the application wise, like move instructions, load instructions, store instructions, arithmetical instructions, logical instructions, and so on, branch instructions, for example. So all these we will discuss in detail in the coming slides. Okay, so this is the sort of a summary of the instructions possible in Cortex M0 or Cortex M0 Plus processor. Both are very similar. Okay, so that's it. With this, let's actually sort of go into some detail of how to go about writing a program, whether it's assembly language or C language. There's a certain way which is followed in ARM, and in fact in most of the modern day processors as well. So this is the typical format. So on the extreme left hand side you will have the label. So the label literally means, if you think from a computer or the microprocessor or microcontroller perspective, label literally means it's an address. Okay, address of this particular instruction. So but it's very difficult for us to put in terms of the entire 32-bit instructions, or 32-bit address, or even the hexadecimal address, because it's very tedious. So we will use English language to represent the address, and for the system, for the microprocessor, it looks like a 32-bit location. Okay, 32-bit address. So label is something which you can give any name, literally any name, but when you compile, when you assemble it, the label gets converted to a location. Okay, so that's the meaning of it. And then of course we have the mnemonic. So this is the instruction. So we'll start with assembly language, and it's very similar in C also, but we'll start with assembly language. We'll program, we'll do experiments in assembly language, and later on we will move to C language. Okay, so we will have a mnemonic. So for example, in our 8-bit microcomputer, the LDA is a mnemonic, add is a mnemonic, sub is a mnemonic, HLT is a mnemonic, out is a mnemonic, and then operand is the registers, or it can be some location or whatever. And then of course we do have comment. So it is interesting to note that the semicolon is like the comment. So whatever you write after the semicolon will look like won't be executed, or won't be considered for compilation, or won't be considered for assembling. Okay, so that's second. So examples. So I think I already mentioned this. So yeah, the first operand will be typically the destination, the target, and the second operand will be the source. So you will be basically operating from the source to the destination. So that's the meaning. Some example will make it very clear. So you really don't know what is this instruction so far, because we didn't introduce the instruction, but what it means actually is move R3. So move this content, whatever content, to R3. Okay, so that's the meaning of it. So set register R3 to this particular value. So that is the meaning. So this is the mnemonic. Okay, so this is the mnemonic. Let me use the pointer. So this guy is the mnemonic. Then this is the operand, which is the destination, and this is operand 2, which is the source, and then this is the command, and there is no label here. So there is no label in this case. Okay, And then the way the format may slightly differ. If you're going for the GNU tool chain, the syntax may be slightly different, but overall it's not really that drastically different. So this is a way. So if you are getting comfortable in the Keel Microvision software, you will be very okay with migrating to some other software, some other assembly linking program. Okay, so this or some other compiler. It's not very difficult to migrate. Okay. So yes, now we'll start. Okay, so please ignore the content. It's not about the content that we are going to discuss now, because the content will be very clear only after you go through the instructions. But the layout, the way we are going to write program, because for example when you write a C program, there is a certain way that you are writing, right? You have the hash include part coming at the top, then you have a void main or int main coming, then you have certain way you write the commands one after the other. So similar to that, the Keel Microvision or the assembly language also has a certain way to go about it. So this is the structure. So we'll explain that in a very nutshell, and then we will take one by one. So labels, we already mentioned that in the previous slide. So please follow this. You put the labels on the extreme left of your program and give at least 2 to 3 tabs ahead. Okay, so this is the labels. Okay, so it should be what I suggest is actually you always write it on the left edge, and then you give some space so that you write every main code after that. Okay, so this gives, it's not for anything but just to give a prettier picture. Okay, so whenever you do this in the lab, please follow this accordingly. And then let me just quickly erase other stuff. So then the next part is of course the code area. So very important. So I mean the keywords are explained in the subsequent slides in some detail. So let me actually go through that again. The next slides will form sort of repetition, so that sort of reiteration happens, and it's good for us, right? Many times we repeat the same thing. Okay, so the major parts, let me use a different color because I'm using this one here. Okay, so let's use this color. Okay, so the entire code area can be started with something like area, code read only. So these are the keywords. So area means it will be defined for something, so this is the name of that area, and it is for code, and this is read only. So that means it will go to the read only part of the memory map, and not only that, it won't be changed on the fly. And then export option is also very important. Okay, so the export option is something like it is for, as usual, if you want to use this file in some other file, you can import and use it readily. So it's basically it's like extern function in C language, so similar to that. Then align is something like you basically sort of put in terms of the alignment of the code, the way the code, this part is label and this part is code, that sort of separation. So it's not mandatory to use, but it's always good to put it across. Then this is a key part, entry. So that is the entry for your code, and there will be an end. So entry to end is always must. So entry will be always followed by end. So this is the entry for the code, so that the processor knows, the microprocessor knows, or the compiler knows rather, not microprocessor, the compiler knows that the code is actually starting from here and ending till here. Okay, so that's the main critical part. And then you have the label, which is the main function. Please don't change this name, because we already saw that in the demo that I showed in the previous lecture, that the name is what the name which is written in the startup code. So if you change the name here, it will never detect a main file and it will cause error. So this is strictly followed. If you really want to change this name, you have to change the name in the startup code also, and then put that name here as well. So this is a label which says to the compiler that this is a main part of the code where it is going to be started, other than this. So basically something like entry is the entry where the code part. So this can have sub functions also, so that will be between this entry and end. But main is where the main function is. Okay, so this main starts, I mean basically something like we write void main, right? So similar to that main is here. And then any function that you write in assembly language will start with PROC, it's like procedure, and there is an NP. So any function, so this is not like entry and end will be unique, it will be only one, but there can be many PROC and many NPs. Okay, so this is something like the main function starts here and main function ends here. That's the meaning of it. So you have another function that will have a PROC and NP. Okay, so you'll understand that when we write many codes in the future. And then you have the code area. You don't know what is happening here, so don't completely understand. So there's no need to understand, so that is fine. And then finally here, for example, there is a branch here. So branch here, that means here itself. So it is like an infinite loop and stays here. It's like the halt operation that we had, similar to that. Okay, so this entire part is something like yeah, so the main code is till here, could say. Okay, so this is the main code, and then we have a data location here, which is actually mentioned. So these two strings are stored. So these are actually some data, and they are also stored in the read-only part. So you're not defining a separate area. There is a way to define a separate area and store the data as well. So that's I will explain to you with an example in one of the subsequent, when we talk about the instructions in the subsequent slides. So we'll take it up there. So overall, so this is the case. So data area, code area, it's all common to you, and this section is something which we call as directives, which direct the area part and some separate things, and then the data is here. Okay, so that's it. So there are so many keywords that you are noticing. So there is area, there is export, there is align, there is entry, there is proc, then there is NP, so many things, right? So DCB, what is this DCB, for example? So all these are actually interesting, and we will have a quick journey into all these in the next few slides. Okay, so the assembly directives, the area, so you can actually read it through. So I don't I'm not going to read it each and every sentence to you, because that's utterly boring. So area indicates the start of a new data or area or code section. Okay, so that's the literal meaning of it. So I'll just quickly show you an example. So here, let me just go to the main part. So here I have an area which is actually sort of basically dealing with the code, which is this part, and there is another area which is actually dealing with the data. So you can do this as well. So this is separately, I'm just redefining the code area and the data area. So you can do this way, or you can actually do as in this code, where it is just continuous. I'm not predefining any separate area, but it just comes under the code area. So both ways we can follow. The thing is, area is the directive which is used to tell the compiler that this is an area which is reserved for code or which is reserved for data, and so on. Okay. Yeah, one more important thing, identified by name and areas within the same source file cannot share the same name. So if you give the name here, you cannot have another area with the same name. So that is the meaning of it. And of course this is sort of, we can say this is not part of code, but it is something like directive, right? Directive to the compiler. It is telling the compiler that this is the area part. And then of course the entry, I think it's pretty clear to you. So a code will have an entry point and an end point. Okay, so these two are associated. So there is an entry point, there is an end point. It should be always like that. Okay, so followed by the other. Exactly one entry directive in an application. Very, very important. Indicates also the first instruction to be executed. So it's like main. And also, you know, so PROC and NP, I hope it's pretty clear to you. So the any function that you take, there will be a PROC and there will be an NP. So it's like the brackets in C, right? You have the start bracket and the end bracket. Similar to that. And then export, import. So export declares a symbol and makes the symbol visible to the linker. That means you can include it at some other. It's like include, right? Same as the, you can put an external function and later on you can include that function as a library. So something like that. So it is to make sure that it is visible to the linker. Okay. So otherwise it is just at the assembler level itself. It won't go to the linker part. So it's just to ensure that. So it's always good if it is particularly important for functions which is there in the separate file, so that you can export it and then you can import in the next file. So that's the advantage that you have. So some people do that. If you can have, as I said before, you can have a mixed code, something like C and the assembly together. So you can write the assembly in a separate file and then export that function, and then you can import that function in the C code. Okay, so many people do that, many, I mean much often. Okay, And then yeah, data allocation is something which is very interesting. So DC, I think I have the next slide. So yeah, it's here. So DCB means it is like defined constant byte, so it reserves 8-bit value. So here for example it's DCD, so it means it's a constant word. It's like 32 bits are reserved for 1, for 2, for 3, 4. So 32 bits are reserved for each. If I change this to basically something like B, so let's say this is instead of D it is B. Okay, so that means it is this one will only take 8 bits. That's the meaning of it. Okay, so I hope it's clear. Some examples are here so that it makes pretty easy for you. So hello, okay, so DCB hello world, so it's like a string being stored in the variable hello. So hello will be a location, please remember that. So hello will be a location in the memory, and that memory location will have this string in the form of 32-bit words, right? So that's the meaning of it. So maybe this H will get converted to ASCII, and that ASCII will occupy 32 bits. That's the meaning of it. Similarly, $DCB, oh DCB actually not, yeah, DCB is a byte, it's 8 bits, yeah, it's direct ASCII. So each one of them will be stored as ASCII, it's not DCD, sorry. $DCB will be like each one will take 8 bits. So it's in the meaning is here. Similarly, scores, this is like 32 bits for each value. Remaining all are self-explanatory for you. Okay, so I hope it's pretty clear. Okay, so moving on. So some other things, so something like, I think this is very common in C also, where you hash define pi is equal to 3.14. so similar to that you can actually, yeah, this is the C way of defining, this is the assembly way of defining. So okay, so you can even include, so there is include command. So EQ is that include you can use. So this is what I was telling, you can define a sub function, a file which you can name it as constant.s, and you can include that in just like the C, right, hash include. Similar to that it's there in assembly as well. So very similar, and there's no need to by heart also, because you can have everything there in the manual. You just need to have that reference ready, and there is no pointing in by heart. I mean, unless you can write faster, that's only advantage, because you can recollect from memory and then write it. But I suggest is like keep the reference manual ready and always use that for whenever you write the program. Okay, so that's it. Okay, so with that we'll stop. Now we are going officially into the instructions, which will let that be a separate lecture itself, which we will cover in this week itself, because these are small, short, crisp lectures. And I hope you are very clear about how to write the program in Keel software. So overall, let me go back to this slide. Yeah, so let me just remove everything, or rather let's put all the things. Yeah, so this is the way, or maybe because let's be cleaner. So this is the way we write the code. So there will be an area part, we can have a separate code and separate data. Then there is important part is this entry. This is the instruction to the processor saying that this entry of the code. Then you have the function, the label here, PROC followed by NP, that forms the entire bracket sort of for the function. Then you write the code inside that. Okay, so that's the literal meaning of it. So this is the way we write, and you will get used to it. So don't worry at this point if you're not understanding, because we will do this in the lab, and you can do it offline as well many times. So you'll get used to it. I hope you're enjoying it. So next lecture we will start with the instructions. Okay, till then it's bye from my side. Thank you.